All right, so I'll be talking about automated verification of parametric channel-based process communication in Go. This is a collaborative effort between Aarhus University and Royal Holloway University of London. So to get started, a brief introduction to Go. Go is a relatively recent imperative and concurrent programming language, and its concurrency model is inspired by communicating sequential processes. In Go, you can very easily create Go routines, lightweight threads in the Go runtime. Oops. By prefixing any function call with the Go keyword. Go routines may then communicate one another by sending and receiving messages over channels. And it is common for Go routines to block while performing these communication operations and waiting for a communicating partner. Then this leads us to one of the challenges of writing concurrent programs in Go, and that is, of course, global deadlock. So you can get into a situation where all Go routines are blocked, and this is called a global deadlock. But fortunately, the global deadlocks are not only detectable by the Go runtime, but they're only rare in practice. A problem that is a bit more pertinent to Go are partial deadlocks, also known in the Go community as Go routine leaks. And these occur when only a strict subset of Go routines are blocked permanently for the remainder of the execution of the program. These are not only common in practice, but because they are not detectable by the Go runtime, they silently waste resources, potentially for very long periods of time. Now, partial deadlocks may be caused by a number of concurrent programming patterns, but the ones we'll be looking at today are those caused by parametric concurrency. And this concept is best illustrated through an example. So here on the right, we have a function called getResults that takes some integer parameter x. Then it creates a channel, and then in a for loop that iterates x times, it creates one Go routine for each iteration, each of which tries to send a message over the channel. Meanwhile, the parent Go routine tries to receive a message over that channel. And what we observe here is that the channel is unbuffered, meaning any send or receive operation is going to block until another Go routine performs the complementary operation. There is one receive operation, and there are either 0 or x send operations. And this is what we mean by parametric concurrency. The concurrent behavior is directed by parameter x, which effectively promotes it to being a concurrency parameter. Now, naturally, when you write a program like this, the desirable property is that it does not have any deadlocks occur at runtime. And is it the case here? Well, the answer is it depends specifically on concurrency parameter x. In this case, there is no partial deadlock in this program, only when x is equal to 1. Any more or less, and either one of the senders or the receiver is going to deadlock. Now, if there was some magical tooltip appearing over the programmer's screen saying that your program is only correct if x is equal to 1, at the time they wrote this, they no doubt would have thought that it's a little bit suspicious. As things were, however, this issue snuck into production code where it laid undetected for over a year, and I guess you can assume that took its toll on operational costs. When it was eventually discovered, this issue was amended by giving the channel a capacity of size x, meaning that you can now perform up to x send operations without blocking any the sender Go routines. And this was good enough because it eliminated the biggest source of partial deadlocks, but it did not cover all the cases, because now if x is 0, you can still deadlock the receiver. And more than that, because x is given as a capacity, if it's a negative value, it may even cause the program to crash. So there is still an implicit constraint at play here, much more relaxed than the one before, and it is that x is greater than or equal to 1, which is unfortunately still not ideal. So if the developers really wanted to make this program foolproof, they should have also guarded against problematic values of x. And by doing this, the implicit constraint is as relaxed as possible. And this is the goal of our work, which is to try to infer these constraints over concurrency parameters and make them explicit statically. Now, there is an existing body of work in terms of static deadlock detection. And the tendency for the existing body of work is to be soundy. That is, it over-approximates execution values, which creates noise. So these techniques also apply some pragmatic heuristics, which are not only unsound, but they're also noisy in their own ways. And especially, this is especially true when dealing with parametric concurrency. However, they do introduce a few useful notions. One of them is that of localized analysis, which is where you take a large program and you split it into fragments. And in our case, a fragment is effectively a set of functions that cover the scope of a channel. And these fragments may then be analyzed in isolation. And another useful technique is to simply abort analysis if precision degrades too highly. And so to tackle this problem of parametric concurrency, we tried to approach it in a different way, which we implemented in a tool called Ginger, which takes these parametric concurrency fragments and tries to express them as Hoare triples and verify for deadlock freedom. Now, the key design elements of Ginger, one of them is that it focuses more on positive feedback, which is to give the developer some feedback that they implemented a parametric concurrency pattern correctly. And another one is that it functions more like a sidekick analysis. So the existing techniques, they are good enough at dealing with non-parametric concurrency fragments, and they can just use Ginger to outsource the parametric ones. And the way Ginger responds to a parametric fragment is either by saying it's correct if it can verify the fragment for all possible inputs, or otherwise try to infer this constraint over concurrency parameters in the form of a precondition of the Hoare triple and give it as feedback to the developer. If both of these fail, it's simply going to assume that the developer is trying to do something clever and say that reserve any judgment. So taken from a high level, the architecture of Ginger is that in the front end, it simply takes these parametric concurrency fragments, and after expressing them as Hoare triples, it tries to verify them by using an off-the-shelf verifier. Before they get passed on to the verifier, however, these concurrency fragments are first translated to a subset of Go called Virgo that focuses specifically on control flow and channel operations. So just to give you an example, the get results function would be translated into Virgo as such, and the concurrency parameter X
still on.
burned out.
Is there a button on your little pocket thing?
Okay, this one work? Oh, sorry. Yeah. So in this case, the concurrency parameter X would appear as a free variable in the Virgo program. So afterwards, the Virgo program is translated into a Hoare triple, which is expressed in Dafny. And the postcondition defined for it is that all the processes in the Virgo program have reached their termination point. So now the idea is to find the precondition that guarantees that the postcondition holds. And this is challenging. Unfortunately, we didn't find a general solution, but we came up with a set of tactics for suggesting preconditions and using that to check. And the most obvious choice is, of course, to check if a program is deadlock-free for all possible inputs. And that will work well for programs which are correct. But, of course, we want to cast a wider net to also catch the motivating example in its two first iterations as well. So ideally, this precondition we find is supposed to be the weakest one, but because there is no general approach to finding the weakest precondition, we can do the next best thing, which is suggest a precondition and then check if it is the weakest. We can do this by exploiting the fact that concurrency parameters in Virgo programs are immutable. So if there is a weakest precondition that guarantees the postcondition after executing the program, instead of checking the Hoare triple you would usually check in this instance, you can simply take that precondition, put it in the postcondition under equivalence with the original postcondition, and if the precondition is the weakest, then this Hoare triple on the bottom will also be verified. So we use this as the basis of our second strategy, and this strategy effectively consists of taking every channel in the Virgo program and then counting how many concurrency operations of each type there are, sends and receives, and then organizing them in this inequality here. And intuitively, think about it like this. If you have some number of receive operations over a channel in the original program, then for the receive operations to not lead to a deadlock, there have to be at least as many sends. Right. So after constructing this proposition for all the channels, we try to verify the program by using this trick to also see whether the precondition we suggested is also the weakest. Failing that, our last line of defense is the third strategy, which basically takes the strategy suggested by the second, the precondition suggested by the second strategy and verifies the Hoare triple as usual, with the caveat that the precondition suggesting here not being checked, guaranteed to be the weakest, might over-constrain the value. Nevertheless, the developer can still use it as feedback, and Ginger will inform them that you will not have any deadlocks if you satisfy this property, but there might be some values which are also safe to use, which are not covered here. So to evaluate Ginger, we let it loose on the code base of Uber, who generously supplied it to us. And in the process, we found 583 parametric concurrency fragments, 378 of which were expressible in the Virgo language. And it turns out that in most cases, if a program is expressible in Virgo, it is also verifiable by one of the three strategies we suggested. And it is so in a reasonable amount of time. That about covers everything. The Ginger implementation is available on GitHub, and I'll leave you with these summary to drive the questions. Thank you.
That's where all the electricity went. Nice work.
Maybe that caused everything to crash earlier. I don't know.
Yeah, nice work. In your tables on the slide before, there were 5 examples that weren't verifiable. 5? Yeah, 5.
Yeah.
Any experience or horror stories there? Or?
So this can happen if so this precondition kind of assumes that channels cannot block each other if there is some kind of dependency going on between like doing some number of channel operations to unblock another. There you might get into a situation where you need a better precondition to actually verify that, like checking some orderings and stuff. Yes? So the fragments are relatively small because that's how developers tend to use them in practice. Maybe a couple of for loops and one channel, let's say. The original code or the translation? Maybe, so compressed down to Virgo, they can be 5, 10 lines. Yeah. So this is in the worst case. Average, we found usually 2 or 3 seconds, and that's usually how long it takes for Dafny to start working.
Yeah, no, there is no doubt that it can explode. So if you were to use this in practice, putting a time limit on it would probably be a good idea. But for those simple fragments, which can be easy to botch, especially by entry-level programmers, it might be useful. Yep. Sorry? We didn't supply the annotations to the developers. We just let it loose and see what it could find.